Functions such as inch mode versus metric mode, or absolute mode versus incremental mode, are specified using a word with a G letter address. The letter M, along with its numerical value, specifies many miscellaneous functions. M words work much like programmable on-off switches for such things as coolant, tool changing, and machine spindle rotation. Some other common letter addresses include the letter N, which is used to specify a sequence number to identify each command line within a program. The letter X, which designates movement along the X-axis. The letter Y, which designates movement along the Y-axis. The letter Z, which designates movement along the Z-axis. The letter S, which specifies spindle speed in revolutions per minute. And the letter F, which specifies feed rate in either inches or millimeters per minute. To obtain optimum end results when programming a machining operation requires a familiarity with certain programmable command parameters, including positioning control, compensations, and special features. Positioning control is the ability to program cutting tool and machine slide movement to predetermined positions along two or more axes simultaneously. The two basic types of positioning control are point-to-point positioning and contouring. Point-to-point positioning involves programming instructions that identify sequentially only the machining positions required. The machine moves rapidly into position point-to-point by movement in one or more axes. Point-to-point positioning refers only to the rapid positioning prior to a machining operation, and not the machining itself, and is used to minimize cycle time between cuts. In contouring, which is also referred to as continuous path machining, cutting operations are performed along controlled paths. Movement along these paths is known as interpolation, which is the process of calculating the intermediate values between points along a programmed path and outputting those values as a precise motion. The two basic types of interpolation are linear interpolation and circular interpolation. Linear interpolation is programmed movement along a straight line. Linear interpolation has only a start point and an end point for the motion and incorporates two or more axes. Circular interpolation is used to machine along a circular path, allowing a radius to be machined. The input required for the circular path includes the coordinates for the end point, the coordinates for the center of the desired circle or its radius, and the direction of the cutting tool motion along the arc. Compensations are used to offset or compensate for tooling-related variations within a part program. Two of the most important compensation types for machining centers include tool length compensation and cutter radius compensation. Most machining operations involve the use of multiple tools of various lengths. For this reason, tool length compensation is utilized to adjust for tool length variations. Cutting tools are first measured. The machining program is then instructed to refer to the various tool length values and compensate accordingly for each tool's length along the Z-axis. Cutter radius, or diameter compensation, is used to compensate for the various milling cutter body diameters and is always read from the center line of the cutting tool. Cutter diameter values are input during setup, and the CNC control modifies the programmed path based on the cutter's actual size. Cutter radius compensation is only used for milling cutters when milling on the periphery of the cutter. Special features are designed to minimize computer numerical control programming errors by simplifying and shortening programs. A common type of special feature is the canned cycle. A canned cycle allows numerous instructions to be programmed, saved, and then input into a part program using only a single command. Hole making is often performed using canned cycles. Once the instructions for the first hole are programmed, any remaining holes can be machined using the same instructions simply by listing their coordinates. All types of hole making and secondary operations can be performed using canned cycles, including drilling, reaming, tapping, and boring. Many CNC controls also have special features designed to easily manipulate programmed motion commands. These motion commands include axis rotation, mirror image, and single direction positioning. The integration of fast, affordable computers and software in computer numerical controls programming has automated many of the time-intensive, complex tasks that were traditionally performed manually. The systems that impact computer numerical controls programming the most include computer-aided design and computer-aided manufacturing. A computer-aided design, or CAD system, involves the use of computers to graphically create geometric product designs and models. These models can be presented in three manners: as a line or wireframe representation, where all part edges are visible as solid lines, or as a surface model, where all visible surfaces are present in the model, or as a solid model, where the model data describes the part's interior volume as well as the part's surfaces. Computer-aided design is extremely useful in generating multiple variations and revisions of part designs. These designs can then be subjected to a variety of engineering analysis for optimization. Once a part design has been reviewed, tested, and approved, the CAD information is translated and then exported to a computer-aided manufacturing or CAM application. Computer-aided manufacturing systems assist in all phases of manufacturing a product, including process planning, production planning, machining, scheduling, management, and quality control. Because of their collective benefits, computer-aided design and computer-aided manufacturing are often combined into a CAD-CAM system. Probably the most important aspect of a CAD-CAM system is its capability of using design data to create and optimize the toolpath for machining. Let's review the material contained in this videotape. Computer numerical controls translate sequential part program instructions or data into output signals that govern machine functions. The common factor that all computer numerically controlled machine types share is their ability to accurately and repeatedly control motion in various directions. Each of these directions of motion is known as an axis. The method of accurate positioning along each axis for all machine types is achieved using the rectangular coordinate system. The rectangular coordinate system allows the mathematical plotting of points in space called coordinates among two or more machine axes. Each coordinate is an actual physical location that the machine is instructed to move through. These coordinates indicate the position of the cutting tool center and are collectively called the tool path. The location where the rectangular coordinate baselines intersect is called program 0, which is a common or reference point from which all coordinates are derived. For any computer numerically controlled machine to function, it must be instructed on what to do using a part program. Part programs are produced using commands or blocks that are composed of words. These words all begin with a letter address and end with a numerical value. Part programs are primarily generated by either manual programming of commands or, more commonly, by the use of computer-aided design and computer-aided manufacturing programming systems. The machining of parts is achieved using machine tools that bring cutting tools into contact with the workpiece. These cutting tools